already, because the order that they have us teach things is you have to do the distance formula before you teach the Pythagorean theorem. Well, before you teach it, yet you need the distance formula to learn the Pythagorean theorem. Remember, who remembers the distance formula? Now, what is it, Rochelle? Is he right? No? What's wrong with it? Who's right here? Oh my goodness, Katie, what do you think? They're both the same thing. How come? Yeah, she's absolutely right. Now what about when he did the y's and then the x's, and she's doing the x's and then the y's? Oh, which property is that? Commutative property of addition. So does it matter if it's added first? And then she's absolutely right. We're squaring it. So what this does is, let's say we were doing the same x, y. Let's say we wanted the distance between these points. I don't know. So if you said y2 minus y1, and if this was your x1 and your y1 and y2's over here. So y2 minus y1, you would have negative 1 squared plus x2, 1 and negative, oh, yeah, both negative 1 squared, right? What she did, it would just be backwards. Hers would be positive. But does it matter? Because we're squaring. So you get the exact same value. So this one's kind of easy to remember. And why is that? It is the Pythagorean theorem. So if these were your 2 points, the way you find A is you take the difference of the y's, and the way you find B is you take the difference of the x's. So if you know the distance formula, you know the Pythagorean theorem. Am I right? And this I cannot remember. I think I showed it to you already. Wizard of Oz, did we do that in here? Yeah. This year? I can't remember. My mind's going blank.
Wizard of Oz was on.
That was last year. All right.
I was watching it.
So let's see. What is the Pythagorean theorem? The Pythagorean theorem states, in a right triangle, the square of the length of the hypotenuse is equal to the sum of the squares of the lengths of the legs. A squared plus b squared equals c squared, where c is the hypotenuse, right? If and only if the triangle is a right triangle. So what does if and only if mean? You're telling me about this thing. Yeah? Yeah, we're a biconditional. So if a squared plus b squared equals c squared, then the triangle is a right triangle. And if it's a right triangle, then a squared plus b squared equals c squared. Biconditional. So we have to kind of know that the shorter sides are called the legs, and the hypotenuse is the longer side. The longer side is always the side opposite the 90. Now, does that kind of make sense? If this one's 90, what do we know about these 2 angles? What do we know about them? Their what? Their sum is 90. What about each of them? Yes, their sum is 90. So what does that mean about each of them? Emily? They're less than 90, right? These have to be acute triangles. Acute angles, rather. So they're always going to be, if we remember our theorem, if we're opening it up wide enough, like these are going to be smaller than the 90-degree angle, which is opening up, you know, a nice wide angle there. So hypotenuse is always the longest side. The other 2 sides are the legs. So our theory says that if you have a right triangle, then a squared plus b squared is c squared. Does it matter if it's a squared plus b squared equals c squared? Can I have b squared plus a squared equals c squared? Is that okay? Commutative property of addition here, just like what we saw in that distance formula. How about this? Is that true? What do you think? Yes? How come? How did I get there? I did. I started with c squared equals a squared plus b squared, and I just subtracted a squared from both sides. Can I subtract b squared from both sides? Yes. So c squared minus b squared is a squared. So we can get different formulas based on this one. Now what if I want to know c? What if I have a value for each of these? How do I find c? So let's start with it looking like this. What if I just want, what's c? Yeah? Well, I'm looking for a general case now. I'm looking for a general case. I know the legs, but I don't know the hypotenuse. Can I come up with a formula? If I have something squared, how do I make it c again? How do I undo squaring something? Yeah? Take the square root of both sides, right? So if I take the square root of both sides, I get c equals the square root of b squared plus b squared. So I've got that formula. So should actually think about this. Do we remember x squared equals 4? How do you find x? What's x? 4. Right? So if you have a situation like this, which I do here, so how come I don't say plus or minus that result? Technically I should, right? That's how math works. If you're squaring something and you're taking square roots, you should get 2 answers. How come I don't do that here? I'm not going to have a negative distance. We are representing like real life situations, the side of a triangle. I can't have one. So it is always understood that we are rejecting the negative result when we're using the Pythagorean Theorem. Let's say I have a leg, but I don't know the hypotenuse for the other leg. So that's this situation here. Maybe I know b squared. I know a squared, but I don't know the other one. So how can I solve for a? What do I do? Yeah? What do I do? Tell me. I want a, not e squared. What would I do? Take the square root of both sides. C squared minus b squared. If we can kind of remember these, finding the different values becomes pretty easy when we work them out. So we can use any of these types of formulas when we're working for missing sides in a right triangle. Of course, we can't really use anything until we've proven it, and there are lots and lots of different proofs of the Pythagorean Theorem. President Garfield was a mathematician on the side. Besides being president of the United States, he was a mathematician. He came up with a proof once. I'm not using his, but you can Google it and you can look at it. This is a very typical one you tend to see. You may have seen it in an earlier grade when maybe they talked about this. This says a squared plus b squared is c squared, so we're using an example. So let's see, I've got 4 units on this side, and I've got 3 units on this side. So if I square that, I square the boxes, right? The boxes represent the actual square. Squaring is an area. So when you square 4, you get 16. Do I have 16 boxes? When you square 3, I get 9 boxes. Add those together, a squared plus b squared. How many boxes do you get? Well, what's 16 plus 9? 25. So here's my 25 boxes, and I arrange them as a 5 by 5. So what's the square root of 25? That's the 5. So a squared plus b squared equals c squared. We just kind of proved it by looking at the boxes that represent the numbers. Now, is there anything wrong with a proof like this? Is there, or is it good? What do you think? Tell me more about this. This is kind of inductive.
Because it's only proving that sides 3, 4, and 5 here.
Yeah, we proved 3, 4, and 5. So would we have to prove this with pretty much every other side? Yeah. So it's not a bad way. This is a very visual proof, so we can kind of see it. But it's not really deductive, which says it's going to work for all cases. Let's see if I can come up with another way of thinking about it. I've drawn another picture here. So these are all squares. This pink square is a square. And then I've got a blue square inside it. And remember how area of a square works? So if you have a square, the area of a square is the side length squared. So we're going to be using that property here. So let's see what we've done. We've broken this apart. We've made a blue square inside it with side C. And we said, all right, so now I have 4 triangles, these little pink triangles. So let's see if I can notice the sides here. Well, the hypotenuse, because it's a square, these are right angles, is length C. And I'm just going to call the place where it hits it A and B. A and B, A and B. So let's see, what's the area of this big square? Well, it's going to be a side squared. How big is each side? Yes, well, each side is a plus b, isn't it? Can you see that? How each one of these is a plus b? Anybody not see why that is? So she's absolutely right. Why don't we just take each side and square it? Isn't that going to be the area of that whole square? Yeah, okay. But the area of the square should also be the sum of the areas of the triangle plus the sum of the blue square, correct? Right? If I add up the areas of these four triangles and these blue squares, I should also get the area. So let's look at the area of each triangle. I'm going to pull one triangle out so I can see it. What's the formula for area of a triangle? What is that, Rachel? 1/2 base times height. So let's see. Well, here's a base and here's a height. So what's the area of one of these triangles? Yeah? 1/2 AB. Now, how many of these triangles do I have? 4 of them. So I really want 4 times these, don't I? I want 4 of 1/2 AB. And what is 4 times 1/2 AB? 4 times 1/2? 2. 2 AB. So that's the area of all of them together. Now I need the area of the blue one also. What's the area of the smaller one? Yeah? Rachel? Yeah? C squared, because each side is C. So C times C will give me that area. So all together, what do I know here? I'm going to add them all up. So the area of the large square, A plus B squared, has to equal the area of the 4 pinks and the blue. Well, the 4 pinks are 2AB, and the blue is C squared. Who's with me so far? We following? All right, so let's see. Let's expand that. How do you expand A plus B squared, remembering that everything gets multiplied by everything else? It's not A squared plus B squared. What is A plus B squared? Yes. Oh, is he right? Where's that 2AB coming from? Remember how to do this? You say A plus B times A plus B. You might have learned a little thing called FOIL. Anybody remember FOIL? Yeah? Or you might have just said just multiple distribution. So we're going to distribute the A. I get A squared plus AB. Then I'm going to distribute the B plus AB plus B squared. Who remembers this? Please tell me everybody remembers this. Barely. She never learned this either. All right, we did do this. All right, so that's this side. And what's going on this side? I haven't really done anything to it yet. What happens if I subtract 2AB from both sides? What's going to happen? Yeah. Yeah, since I have the same thing on both sides, if I subtract them out, they kind of disappear. And what am I left with? A squared plus B squared equals C squared. There it is. Oh, that's special. And so for each of these triangles, A squared plus B squared is C squared. So that's kind of cool. It's a little bit more deductive. It is. And there are all different kinds of proofs that are kind of variations on this, where they play with different shapes, and we come back and we see that A squared plus B squared equals C squared. This is one of the simpler ones I can find for it. So I'm convinced. Anybody else convinced? Just a few of you. Some of us are not convinced. Thomas, not convinced. All right, so examples, how do we find the missing sides of these? So first of all, you have to decide A, B, and C. I always start with which one is C, the hypotenuse. So in this one, which one is C? The X. Does it matter who's A and who's B? No. So A squared plus B squared equals C squared. This is on here someplace. It's somewhere over here. I'll look at it. Yeah, it's right on the front page there. So let's see, 8 squared plus 6 squared equals X squared. Well, let's see, that's 64 plus 36 equals X squared. 64 plus 36, 100 equals X squared. If X squared is 100, what's X? 10. That could be minus 10, right? Because to solve this algebraically, you get plus or minus 10. We automatically reject that minus 10 because I can't have a negative side. So X is 10. Oh, that's easy. Okay, let's try this want to write that there so I remember it. A squared plus b squared is c squared. Well, let's just call it A rather than b. It doesn't matter who's A and who's b. So x squared plus 9 is 25. Subtract 9 from both sides. 16. If x squared is 16, what's x? 4. And again, we realize we're rejecting the negative 4. That is part of the solution as well. So that's a 4. Now we could have done the same thing we talked about before. If we can remember that a side is the square root of c squared minus b squared, I can really just use my calculator too. Eventually, right? At first I do want you writing them all out, but to do them quickly, you can say, okay, I want the square root of c squared, 25, actually I'll write it out, 6 squared, 5 squared minus 3 squared. And it just tells me, which is kind of nice. But I would say the whole, maybe use the calculator to check it first. I really want us to see this, really get that. Yeah. Well, x squared is 16, which means what? X is plus or minus 4. Because isn't minus 4 times minus 4, 16? Yeah. So I have two answers. And so, but can negative 4 be a possibility when I'm talking about the side of a triangle? So you reject that one. Let's see this guy here. Let's see, c is my 10. So x squared plus 5 squared is 10 squared. X squared equals 25, I'm sorry, plus 25 equals 100. Subtract the 25. So x is going to be, we're going to just take the positive root of 75. Well, that's not a perfect square. So what can I do here if I want the exact length? I want the exact length. What do I do? Well, that will give me an estimate. So yeah, I could say, gee, square root of 75 is, let's see what that is. And I'm always going to get some irrational number here, so I'm going to have to estimate. So what is it to the nearest 10? Nearest 10, right? One decimal place. What is it? 8.7. Tenth is one decimal place. So that's approximately 8.7. Approximately. But I want the exact. What am I going to do to find the exact?
Is there any circuit square multiple?
Yes.
There are.
What is this?
So it would be x equals 25 square root of 25 times 3.
Okay.
Square root of 25, 5.
Now, what do I mean by exact solution versus estimate? Exact solution is this. I'm not estimating. It is 5 times square root of 3. Square root of 3 is 1.732, blah, 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 blah. It goes forever. I can't write it as a decimal. I can't do it. I have to estimate it. So if the answer says round to the nearest 10 or estimate the answer, then it's telling you to go ahead and give me a decimal approximation. If it says find the exact solution, I want the square root. But if you have a square root, you always have to express it in simplest form. Make sense? Okay. Alrighty. Word problems, these are all about real life, because you can actually use this in real life, because we must know this. This is important to know. If you've got a ladder, and it's resting against the side of the house, and the base of the ladder is 4 feet away from the house, and I've drawn the picture for you. Usually you have to draw the picture. How high above the ground, and that would be this, is the ladder? How high above the ground is the top of the ladder? So being able to read these questions and kind of draw the picture yourself is a good skill. So we're starting out by giving you the picture. So do you see our right triangle? Yes. So let's see, which is the hypotenuse? You see? The x, the 4, and the 16. There? Where'd we go? We here? Good. All right, so yeah, it's the C. So what do I have here? X squared plus 4 squared is 16 squared, right? So let's see. I could do it this way. X squared equals 16 squared minus 4 squared. X is going to be the square root of this whole thing. Now what is the 16 squared? And what is 4 squared? And then what's that? 240. Oh my goodness. So let's see. That is the same as 4 times 60. I don't know, you're 60 16 would be, I'd probably be late in that. So, let's see. 16, let's see, she has 2, 3, is that, maybe that's it? No, there's more than that.
No,
60 is, 10 times, 12 times 5, right? What? 16 and 50? 16 and 50. Oh, okay, we're doing this one. I'm working from here. I went too small, so that's gonna be 12 times 5. So that's 4 times 3. So the square root of 4 is 2, that comes out. 4 at 15? Exact, right? Now this is a word problem. So if some painter needed to know this, I need to know how high that window is. Yeah, I got it for you, Mac. It's 4 square root of 15 feet. Is that how we speak in real life?
yes.
Well, except for Asa. He does speak in square roots, that I know. But the rest of us probably would not. You have a painter at your house or maybe somebody working the brickwork. No. So this would probably be one where you're going to say, nobody talks like that. So let's see what that is, approximately. 15.49. So what probably would the person say? How much rounding should we do? Yeah, probably 15.5. That's about 15 and a half feet. Word problems we tend to do with the decimal estimate. It's usually to the nearest number. If this was a building that was like 20,000 feet high, wow, that's a building. Oh, we should build one like that, 20,000 feet high. We're probably not going to round to the nearest half or the nearest tenth, but for something like this, we might. So word problems you tend to work out to the decimal. All right. Other examples. Find the area of an isosceles triangles with these lengths, 10, 13, and 13. So 13 and 13 are my, my congruent sides, and then I've got these sides here. This is interesting. How come if I know side length is 10, how come I can say 5 and 5? Why can I do that? Why is it a perpendicular bisector? Well, I know it is, but how do I know it's a perpendicular bisector? Because remember, they don't have to go to the vertex. Perpendicular bisector doesn't have to hit the vertex. Yeah.
It's,
Why? Why is it doing that? How do I know an isosceles triangle it does that? How do I know? I wish there was a way to prove these two triangles congruent, because then I would know by CPCTC that they have to be congruent. Yeah, Emily.
If the angles are congruent, because
Okay, so she felt this way. Say, because it's isosceles, these two things are congruent. Yeah, so what do you have?
and then
Because this is a right angle. What do I know about this one?
it's a angle
So what do I have here? Angle, angle, side, side, angle, angle. Could have done it another way. You could have said, oh, look at this one. So I've got a hypotenuse and I've got a leg. So there are multiple ways to prove these triangles congruent. So it must be that this equals that by CPCTC, so I know I can split them apart. So, yay, we can do that with an isosceles triangle. So anyway, area equals 1/2 base times height. Find the length of the altitude. Now an altitude is your height. It's going to be how high from the top of the triangle to the bottom. Now I know this part's 5, and I know this part's 13. Can I find this guy? Yeah. Yeah, let's call that one X. How? How can I do that? How do I do that? Pythagorean Theorem. We look here and we see this triangle over here. It is a right triangle. So what do I know and what do I not know? Like which is C? Which side of this half triangle here within the big triangle? Which one is the hypotenuse, the C? Which one do you think? Yeah, how come? Oh no, it looks it. How come? It's opposite the right angle. You look for the side opposite. There's my C. So it doesn't really matter who's A and B. So let's see. A squared plus 5 squared is 13 squared. A squared plus 25 is 166. Well, that means that A squared is subtract 25 from both sides. 144. So what's A? 12. So that's my altitude, the height. And now I can find my area. Area is 1/2 base times height, which is 1/2. My base is this whole thing, 10. My height is 12. 1/2 of 10 is 5 times 12 is 60 square meters. That should be my area. What do you think? Questions? Yeah? How did I do what? How do I find the area? 1/2 base times height. So 1/2, my base is the this part here, 10, and then this is my height of 12. 1/2 of 10. These are multiplies, right? 1/2 times 10 is 5 times 12 is 60. Yeah. All right. So let's see what else we have here. Pythagorean triples. Now some of these, a little secret here is I already knew this was 12 before we did it, because we have this idea of Pythagorean triples. Pythagorean triples are 3 positive integers that can be used for the length of a right triangle. Notice that it's positive integers. So can I have like 1/2 as part of a Pythagorean triple? No. Can I have -5? No, it makes no sense anyway. So positive integers. 3, 4, 5 is an example of a Pythagorean triple. 3 squared plus 4 squared equals 5 squared. It works. So if you have 2 integers, square them, add them, and it equals a third squared, great. The longest side is always your hypotenuse, right? Primitive triples are those with sides that are co-prime. Co-prime means there are no common factors other than 1. This is called a primitive triple. What factors are in common between 3, 4, and 5? This one's 1 and 3. I'm just looking at all their factors. What factors do they have in common? Yeah, 1. So if that's the situation, you have what's called a primitive triple. Now you can have other triples that aren't primitive by applying the scale factor. So if I have 3, 4, 5, what do I mean by applying a scale factor? Multiply them all by the same thing. So if my scale factor is 2, multiply them all by 2, and I have a, oops, that's a 2, that's a 10. I have another Pythagorean triple. This will work, 6, 8, 10. 6 squared plus 8 squared, well, that's 36 plus 64. Is that the same as 10 squared? Yes. They work. So if you have a primitive triple, you have an infinite number of other triples that you can find. Well, 6, 8, 10. You can multiply by 3. 9, 12, 15. That's going to be another Pythagorean triple. So we've got a bunch of these. Now I'm looking at the table that you have on the bottom. These are some of the primitive triples. I'm giving you a few that you should probably know. 3, 4, 5 is one you need to know instantly. 5, 12, 13. 8, 15, 17. 7, 24, 25. Now I went ahead and I applied the scale factors for 3, 4, 5. So what did I do? 1 to 2 says multiply them all by 2. The 1 to 3 says multiply them all by 3. Multiply them all by 4. Multiply them all by 5. I want you to fill in this table. So for example, 5, 12, 13. If you multiply them all by 2, what do you get? 10, 24. I want you to fill in the table. All right, so you're going to get a whole list of triples. Go ahead and fill that in. I filled in my table. Hopefully, they somewhat match. If you kind of made a mistake, let me know. We match? No, where'd you go? Everybody's gone. I'm in an empty room right now. Those of you listening at home on this recorded version, everybody has left. It's just me. No, they're here. They're not talking to me. Those of you on vacation a day early and be ashamed of yourselves for that.
2 days early.
2 days early, exactly. So anyway, it's easy, right? So all I have to do is just memorize an infinite number of numbers here, and I can easily find a triangle without having to use Pythagorean Theorem. Do I have to memorize an infinite number of these things?
Yes.
Yes. No! All right, so what should I memorize, though? The primitives. So the idea is if you know the primitives, I can tell if I'm looking at a triple, if it's a multiple. Yeah. If it's a 3, 4, 5 triangle, and this is a test, and I gave you this, I really just expect you to put a 5 in. Yeah, I mean, there's no work to really show. But if it was something like what we're going to look at, I might expect to see something. So let me just go to the next thing here. Oh yeah, let me talk about this for a second. It's a little aside. This is just something cool I found, that you can actually create your own primitive triples. So the idea is a set of three numbers here. If you multiply the first two and you apply these little expressions to them, you can get a triple. So A and B are odd and relatively prime. So that means that if you pick two numbers, they're integers, positive integers, and the only factor they have in common is 1, then you can create a triple. Let's see if it works with 2, 4, and 5. So if I pick 3 and 4 as A and B, and I'm trying to find the fourth thing, this says that you do 3 times 4 to get the first one, A squared minus B squared. So let's see. That's what, 16 minus 9. All right. Let me give you the example I have here. 9 and 5. So here's how it works. So you take 9 and 5. So that's 45. 9 squared minus 5 squared over 2. That's 56 over 2. 9 squared plus 5 squared over 2. You get 45, 28, 53. And this is a primitive triple. So you can actually create them just out of thin air. Oh man, can you do this one? What have you done here? This one, I think, yeah, it has to be, okay, so this is 4 and this is 3. I'm going to have to do it that way. So 4 squared, 16 minus 9. How come that's not working? 16 minus 9 is 5. Yeah, it's not working now. I guess it doesn't work for that. 1 has to be, I don't know why it's not working. Anyway, so maybe it's not a good one. Anyway, I thought this was kind of neat. But using them. So here's an example. Find the third side of a right triangle with two legs. Now, I could use the Pythagorean Theorem. There is nothing wrong with using the Pythagorean Theorem. The numbers start getting big. I guess in the days before calculators, this would have been a huge deal. So what would I do without having to use the calculator for this? Is there a greatest common factor between 48 and 20?
2.
I can look at all of them, right? 4, 5, 10, 2. This one's got a lot of factors. 4, 6, 8. You guys know how to factor like this?
Yeah.
Okay. What's the greatest common factor? 4. Greatest common factor between 20 and 40 is 4. So what I'm going to do is compare with the primitive. So I'm going to divide by 4. What's 48 divided by 4? What is 20 divided by 4? Oh, let me see. Let me go back to my primitive triples. Oh, wait. 5, 12. What's the other one? 13. 5, 12, 13. So it matches a 5, 12, 13 on a triple. So then what do I do? Apply the factor, this thing, to the 13. So what's 13 times 4? 52. So then what's the third side? 52. So I don't even have to use the Pythagorean Theorem if I know that it's a triple. And you know it's a triple, and you get good at this. So for example, these are the same ones we did earlier. They're the exact same ones. 6, 8 blank. Well, what's the greatest common factor between 6 and 8? 2. So divide by 2, and I get 3. Divide by 2, and I get 4. So this is a 3, 4, 5 triangle. Reapply the scale factor, 10. So this is how we would show work if I'm using triples, but it's not a primitive. Let's see about this one. 3 and 5. Wait a second. What's that triple? 3, 5. What is that one? 3, 4, 5. There's like no work to do for that one. Now this one, if I go and I reduce it, I see a common factor of 5. I don't have a triple 1 blank 5. I know this one is going to be a little work. I'm going to have to use it. 2. I'm going to have to use the Pythagorean Theorem for this one, and we did. And I forgot what we got. 5 and 3. But we'll be seeing this one a little bit later also. Okay. So let's see. Oh, I don't have any tries here? No, I do. How come my tries aren't in here? That's a problem. Go ahead and do those tries on the middle of page 2 here. or am I doing this right? Do we disagree on any of them? Yeah. How to do this? Yeah, so what I did with this one is I said, 27 and 45, they have a common factor of 9, right? So I divided them both by 9. And this one became 3, and this one became 5. And then I'm like, hey, 3 blank 5, what's that go? What is that one? 4. 3, 4, 5 triangle. How am I going to get back? Multiply this one by 9, and that's where the 36 came from. So we're noticing that these are the primitive triples that go with this one. This one, I divided by 4 on this one. Yeah? And so you get 24 and 25. You go back, look at your little table here. 24, 25. Oh, wait, that's 7. 7, 24, 25. So then I can just multiply by 4. 65. Oh, wait a second, 13. Divide by 13, right? I think that works. And that becomes a 5. And that becomes a 13. Well, do I have a triangle? 5 something 13. Yes! 5, 12, 13. So then I'm going to multiply that by 13, and hopefully I multiplied it by right. I got 156. What's going on with this guy? Looks like 7. So that becomes divide by 7, divide by 7. That's 7. Oh, wait, this is another 7, 24, 25. So now I can multiply by 7, and I get back up here. So without having to use the Pythagorean Theorem, but knowing my primitives now, you just have to remember your primitive triples, you can get back there. Yeah? I guess you could. I mean, it's not against the law. We tend to write it in size order. You just tend, and if you're never going to say, oh, it's a 5, 4, 3 triangle. You always say 3, 4, 5 triangle. It's not that it's wrong. Yeah, I guess it's more like a convention kind of thing. Alrighty. Let's see what we got here. Classifying triangles based on side. So we're on the back here. We're in the home stretch. If a squared plus b squared is c squared, then it's a right triangle, right? This is the Pythagorean Theorem. And I guess this is the converse. I personally don't care converse, not converse. But this is the theorem. It's a biconditional. Well, what happens if a squared plus b squared is bigger than c squared? So it's like you took this, and I kind of shrunk my c. I shrunk it a little bit. So if you shrink c, what happens to these two sides? They kind of cave in on each other. So because this is now, let's say I made this 9. So a squared plus b squared is less than c squared, isn't it? So now that means that this 6 kind of gets pushed in. And this gets pushed in a little bit. So what happened to my 90-degree angle? What kind of an angle is it? It's smaller than 90, so it's going to be an acute angle. Well, what if a squared plus b squared is less than c squared? So basically, I took my nice pretty right triangle, and I said, well, why don't I make this a little bit bigger? So I kind of like stretched this out. So now what happened to my nice little sides here? So what happened to my 90-degree angle? They got bigger. It's obtuse. So finding a squared and b plus b squared and finding c squared will tell me if I have a right angle, an acute angle, and an obtuse angle. This can be a little confusing. Now, I'm not one for tricks, right? You've had me before, you know that I don't like tricks. This one, I got a trick for you. You're welcome. All right, so here it is. I hate myself for it, but I'm doing it anyway. If a squared, we can remember equals c squared, right? Can we remember a squared plus b squared equals c squared will be a right triangle? Can we remember that? Go like this. Perfect. Now, a squared plus b squared. If you think of this thing as a little arrow, it's pointing to the c. So it's going to be acute. I hate myself for this. Just so you know. If it's less than, see where my arrow's pointing to? Pointing to the B. For obtuse. See what's happening? You see it? So if you, thank you. It's never fought it for me before, ever. It's usually quite the opposite. All right. So the other thing you got to watch out for is if I give you some sides and I say, is this acute? Is it right? Is it obtuse? First of all, make sure it's a triangle, because it could be a trick. So let's see. Decide whether the number 22, 43, and 49 can represent the sides of a triangle. So you do that first. Remember how we did that triangle inequalities? How do I know if this is a triangle or not? How do you tell if 22, 43, 49 makes a triangle? How do you remember how to do that? That's you. Michelle.
The sum of the two sides has to be
Bigger, right? The sum of the two sides has to be bigger than the third. What's 22 plus 43? Is it bigger than 49? Yeah, and I mean, you really should check them all, but that kind of works, right? So is this a triangle?
Yes.
Yes. So you do that first. Is it a right triangle, an acute triangle, or an obtuse triangle? So we are going to be looking at a squared plus b squared and c squared. Now, how do I know who's a and b and who's c? Well, I kind of do. How do I know? The biggest one, that's your c, right? So let's see, a squared plus b squared is what? 22 squared plus 43 squared, and c squared is 49 squared. Now we take out our calculator. So let's see, I think I've done this already. I got, and you check me, somebody doing this with me? Somebody do it. Because I want to make sure, I did this quickly and I might have made a mistake. Did I do them right? So you're basically going to find a squared plus b squared, and you're going to find c squared. So I've got 2333 and 2401. So is that an equal or less than or greater than? 2,333 is less than 2,401, correct? So what kind of triangle do I have? Obtuse. How do we know? Yeah. Point it to the B. Point it to the B. Yeah. All right. Or if you really want to think about it, because my a squared plus b squared in an obtuse, it's like I shrunk. See, I made it smaller, so that's going to widen up your 90-degree angle to be obtuse. Yeah. What? Well, I don't know what C was to begin with, but basically what happened was C may have been. So they need to stretch out, and that becomes bigger than 90. Wait, how do you know? What? How do I know what? What? Huh?
How do you know it's not two?
Because a squared plus b squared is less than c squared. And if a squared plus b squared is less than c squared, I have an obtuse. The little trick says, if you're pointing to the b, it's obtuse. Oh, you tried. Your turn. You get these? Let's see. What did I get? I got the first one to be obtuse. Are there questions, and particularly C and D? Yeah, which one? Both. All right. So I like making a little a squared plus b squared section, and then I make a little c squared section. What is the square root of 14 times the square root of 14? 14. Right? Square root of 14, by definition, if you multiply it by itself, you get back to 14. What about 4? How do you square this thing? How do you square that guy? Do you remember the rule that says if you have a product and you're raising it to a power, it's both those things squared? So what's 4 squared? 16. Square root of 2 times square root of 2 is 2. 16 times 2, 32. Let's see, 6 times 6 is 36. 14 plus 32 is what, 46? I think? Doesn't matter, I know it's bigger than 36. So this one is going to be cubed, it's pointed to the C. This one is going to be a squared plus b squared. 25 plus 100, correct? C squared. What's the square root of 230 times the square root of 230? 230. They're actually kind of easier in a way. That one's 125. That one's 230. Well, that one's bigger. It's pointing to the B, obtuse. Yeah.
First one, that thing set the side level of the triangle.
Oh yes. Are any of them not triangles?
D.
Is D not a triangle? What is the square root of 230? Well, it's a big number, right? What is it? Ah, good point. Not a triangle. Because 5 and 10 is 15 is smaller than this one. Good one. But if it had been, that's how you would do it. The rest of